Sounds exciting.
Thank you. Thank you very much. Sorry about the bad handwriting. It's still a font, but I, before I forget, many thanks to the organizers for inviting me here. It's a privilege to be a part of the workshop. It's also very special because the postdoctoral stint that you mentioned, I did here, mostly at CSA, and those were a wonderful 3 years. So that I'm very grateful for, and it's lovely to be back. So today I'll be talking about firefighting with critical nodes. So I have a bit of a vested interest in having chosen this because it's a problem that's pretty new to me, and I'm pretty sure most of you know more about it than I do. So I'm hoping that we will have interesting coffee/dinner table conversations about this, and I can hopefully pick up some tips on what to do next. We just worked on this when MS Ramanujan here was visiting us at IIT Gandhinagar, and this is joint work also with Jayesh and Anirban. So Anirban is also a colleague at IIT Gandhinagar, and Jayesh is a graduate student in his group. So Jayesh, a lot of his work, a lot of his PhD work is about just understanding temporal processes on graphs, and he studies various kind of processes, mostly motivated by stuff happening on social networks. He does a lot of work studying Twitter and so forth. And was during one of his presentations that we felt that maybe we could actually frame some of these processes as something that's traditionally called the firefighting problem, and we thought we'll dig a little bit deeper. MSR, on the other hand, I think this is a classic case of when the main tool you have a hammer, every problem looks like a nail. And MSR, during the course of his PhD, had become something of a specialist in using a technique called important separators. So when we got together, we started thinking about whether important separators could be useful for solving firefighting, and it turned out that the answer was in the affirmative, which we thought was interesting. So that's the connection that I'm going to try and establish now. It shouldn't take too long, so let's get started. So I'm going to define the firefighting game, if you like, or the process. So as with most of the other talks today, we're going to start with a graph. And this is, imagine a clock running in the background. And at time step 0, one of the vertices, as you might have guessed, catches fire. Okay, and it's a turn-based game. So you place firefighters on the vertices of this graph to combat the fire. So in alternate steps, you get to pick a vertex and protect it. So for instance here, I've chosen to place a firefighter on the vertex that's now labeled green. So you get to, in this model, deploy one firefighter in one step, but this being a very well studied problem, people have tinkered with this as well, and we will maybe chat about that a bit at the end. But right now it's just one firefighter in your turn. In the next step, every vertex that's adjacent to a burning vertex that is not protected by a firefighter also catches fire. So the fire is constantly spreading BFS style through the graph. Okay, so for instance here, these vertices now catch fire, and now I get to place a firefighter again. Sorry, I'm going to quickly, so that's where I place the firefighter, and now this vertex catches fire. I place a firefighter there, and at this point, you can probably sense that the fire is throttled and it can't spread anymore. So there is no vertex that is adjacent to a burning vertex that's not burning or not already protected. So at this point, the game's done. And these remaining vertices are what we call protected vertices because they kind of were not affected by the fire. So that's the legend. I'm sorry, I think I got the terms mixed up. So the protected vertices are the ones with the firefighters, and the rest are saved. So there are several optimization goals with this game. A natural one may be to maximize the number of vertices that you save. So place firefighters with the goal of maximizing the number of saved vertices. You may want to minimize the number of vertices that were harmed in the process, and these seem like related goals, but they may end up requiring different strategies. You might also want to minimize the number of firefighters that you deploy, because possibly you could view this as an expensive resource. And the asterisk there is to just again remind ourselves that you don't have to necessarily deploy one firefighter in every turn. So there are people who like to just optimize the number of firefighters that you have to deploy in every turn, but the total number can be as much as you like. People also look at minimizing the total number of rounds. So this is a pretty destructive game, so you don't want it to go on for too long. So that's something that people consider too. Yet another objective is to think about saving some specific vertices that you really care about. So these could be some VIP locations in your network, and you really don't want them to catch fire. So this is mostly the version that we will be concentrating on. And there's been a bunch of work on this prior, and this is one of those problems that tends to be quite hard even on fairly structured instances. So even on trees with constant maximum degree, it's NP hard to save a specific critical set unless the fire starts at a vertex that has degree 2, which is a pretty special case. And there has been some work done on approximation, but I'll be talking a little bit about looking at this from the framework of parameterized algorithms, where our goal is to essentially come up with algorithms whose running times look like this. Essentially, we are willing to take an exponential or worse sort of a hit on something that we declare as a parameter, and we really want the running time to be polynomial in the total size of the input. So if you haven't seen this before, it may look a little bit funny, but the idea is that think of this as a coping strategy for NP-hard problems, where you're just really trying to formalize the idea of what is the largest class of instances on which I can solve my problem efficiently. So imagine that you have an algorithm that runs in time 2 to the k times n squared. This is effectively a quadratic running time for all graphs where the value of k is something like order log n. Right? So if you have 2 to the k and k, the value of k, I mean, somehow you are in a situation where k is never more than log n, then this is effectively, this is effectively a cubic time algorithm in the worst case. So that's one way to look at it, that you're trying to get an algorithm that has a decent running time most of the time, hopefully in the practical situations that you are in, your parameter has been chosen so that it is small enough for these algorithms to be nice. We often call these problems fixed parameter tractable because they are tractable for fixed values of the parameter. It's slightly ambiguous terminology, I have to admit, because even if you had a running time which looked like n to the k, that would still look like a polynomial bound for every fixed k, except that it's going to be a different polynomial for different k's. So that in our world is not considered tractable. So we want the polynomial to be, we want the polynomial to be quite independent of k. We don't want the polynomial bound to change with changing k. And just like in the world of classical complexity, we parameterized folks have a hardness mechanism, so not all problems are nice for all parameters. So you can, in some situations, establish that such algorithms are unlikely to exist. Usually you are going up not against P versus NP, but you're going up against ETH. That's the kind of hardness framework that we have. We won't really be needing it, so I won't say much more about it, but this is just in case anyone's interested. So what are the kind of parameters that we want to consider for firefighting? There are several natural ones. So for instance, maybe the number of critical nodes is a reasonable parameter. Maybe there are only a few things that you want to save, and you would be interested in FPT algorithms. Heard some mentions of tree width and path width. This is a very popular structural parameter as far as graph problems go. So maybe you want to parameterize by the tree width or the path width or the clique width, any of these width-based parameters. So you're just trying to parameterize by the structure of the underlying network. Maybe you want to parameterize by the number of firefighters. This is what would probably go by as what we call a standard parameter, which is essentially any notion of budget, any notion of the thing that you're trying to optimize. When you parameterize by that, that's called, colloquially called the standard parameter. So in this case, I would think of this as a standard parameter. And there are several other parameters that we will perhaps come back to later, but let me just walk you through what happens for the first three. So when we talk about the number of critical nodes, it turns out that this problem is as hard as finding a large clique in a graph, which in the parameterized world just makes it an intractable problem. So our hopes are a little bit dashed here. As for tree width, again, the problem is known already to be hard for trees. This is again when you're trying to save a critical set of nodes. This is, as we've just seen, NP hard on trees. So it's, there is again no hope for a FPT algorithm parameterized by tree width because the problem is already hard for constant values of the parameter. So this is also turning out to be a little bit sad. But with respect to the number of firefighters, it turns out that things start looking up a bit, and that's what most of the rest of this talk is going to be about. And here, as I said, maybe we'll have a little more to say about this towards the end. Let me now talk about separators, which is going to be our main choice of hammer for this problem. So first, let me just talk about XY separators. So we have two typically disjoint subsets of vertices, X and Y. And a separator is simply, XY separator is simply a subset of vertices, which when you delete from the graph, leaves you in a situation where you can't get from X to Y. So there is no path in G minus S from any vertex in X to any vertex in Y. We will use this notation to refer to everything that you can reach from X once S is gone. So this is the reachability set of X with respect to the separator S. Notice that this yellow box does not intersect with that blue box if S is a XY separator. So you cannot reach Y from X once S is gone. So that's the notion of a reachability set. We also quickly mention what it means for one separator to cover another one. So a separator T, again, so I may not always qualify that I'm talking about XY separators. So this is implicit. I'm talking about XY separators. So T covers S if the reachability of X with respect to T is a superset of the reachability of X with respect to S. So that's the picture. And this turns out to be a useful concept for defining domination and in due course a notion of importance separators. So we say that T dominates S if it covers S and is also competitive with S in terms of size. Okay. So in this case, T does not dominate S because it's actually a bigger set. But if the size of T is at most the size of S and T covers S, then we say that T dominates S. So this one's doing a little bit better. This one would work as well. Okay, so that's the notion of a separator dominating another one, is that you basically, you're as good as the other guy in terms of size, and you leave behind a larger reachability set from the X side. That's domination. A separator is important if it is dominating and if it's minimal at the same time. So again, the intuition here is that, well, between X and Y, when we are talking about folks that are parading as XY separators, we are really interested for various reasons in separators that are as far away from X as possible and consequently as close to Y as possible. This is just one way to sort of formalize this intuition. So T is important if it's not dominated by anybody and if it's also minimal. So in some sense, if there was another separator with a larger reachability set, then that would be the important guy, not the former one in the picture. So that's kind of the intuition. So it turns out that importance separators were introduced by several people, but I think goes back to a paper by Daniel Marks when he was considering the multi-way cut problem, which, correct me if I'm wrong because I always get this mixed up. I think that's the one where you're trying to separate all pairs of terminals, all pairs of k terminals, and I think he was studying the parameterized complexity of this problem, and importance separators came up. And it turned out that importance separators were actually very, very useful for several other problems which had a cut flavor, which sometimes didn't have one but reduced, as we saw in one of the earlier talks today, is reduced to a cut kind of situation. One of the famous examples, I believe, is almost 2-sat, where you want to know if you can delete a small number of clauses from a 2-sat formula to make it satisfiable. Turns out that one of the best known algorithms at the moment uses importance separator machinery, and so on. So, so it was well named, I suppose, and one of the reasons they're interesting is because there aren't too many of them. So this is one of the really nice things. So the number of importance separators of size at most k is bounded by a function that only involves k, and in particular does not involve n. Right. So for instance, in this graph, if you had to count the number of separators between the two black vertices that are of size 2, there would be 2 to the n by 2 of them roughly, because you have to kill each of these paths, right? And you have a choice of picking one of each of these endpoints, right? So they're exponential in n many of these separators of size n by 2, but you'll see that there's only one that's important, the one that's pushed all the way to the right. So yeah, 2 to the n by 2 separators if you didn't care about importance, but only one when you insist on importance. This bound happens to be tight up to polynomial factors, so you could construct an example which looks more or less like a tree to see that the number of importance separators sort of corresponds to the Catalan numbers, so you cannot do much better. I'm not going to go into the details of this specific example, but this is just to say that the bounds are pretty much tight. Okay. So where do separators and possibly importance separators aid the firefighting problem? So, so if you think about what's going on in firefighting, you have a source vertex where the fire has started, and you have a set of critical vertices that you're trying to protect. If you look at the set of vertices on which you place firefighters, then it's fairly easy to check that this is a source critical node separator, because if the firefighters didn't manage to cut off supply from the source of the fire to the critical nodes, then you would still have a path along which the fire could reach one of the critical nodes. So this is the first simple but perhaps key observation, that a solution to the firefighting problem is always a separator of some sort. But why are important separators interesting? This is going to be very wishy-washy. This is just some of the very early thoughts that we were having when we were hoping to make a connection with important separators. So I guess a positive is that somehow, so if we think about separators that separate the source of the fire from the critical nodes that are important, so they're as close as possible to the critical nodes, then perhaps such separators give us some time. So the idea would be to place firefighters on the vertices of the separator, and because they're far away from the source of the fire, maybe we have this is our best shot in terms of having time to place firefighters on these nodes. They would perhaps survive all the way till the end. On the other hand, because we are we're kind of obsessed with just using the importance separator, we may not be able to catch some short paths from the source of the fire to the set of critical nodes, which may not be intercepted by our importance separator. So I think this is a little easier seen with an example. So let's look at this sort of a situation. This would be an important ST separator. So let's think of S as the source of the fire and T as the only critical node that we are interested in saving. Of course, you might just be puzzled by the fact that there's only one critical node to save, in which case why don't we just use a firefighter on that node and be done with it. You can imagine that this vertex is replicated sufficiently many times for that to be too expensive. It's just that we wanted to keep this example clean. Somehow it's too expensive to place a firefighter on this vertex, so we have to make do with something smarter. If we try to use the importance separator, then let's just try and see what happens. So round one, the fire started at the source, and then let's say that we place a firefighter here. I think it's easy to convince yourself that I'm not cheating by going in a particular order. No matter what you do with the importance separator, you're going to run into some kind of trouble with this particular example. But here is one demonstration. So let's say we place a firefighter here. The fire, meanwhile, has touched all of these guys, and now I place a firefighter here. And now the fire is looking pretty dangerous because it's actually hit by now already the importance separator. And now no matter what I do, my critical nodes already caught fire. Okay, so this was sort of in some sense a poor strategy, and you can check that this is going to be a poor strategy no matter which order you choose to place the firefighters in on the importance separator vertices. All right. So on the other hand, this is not to say that this instance doesn't have a decent solution. This is a perfectly reasonable one that just cascades through this diagonal line of vertices here. So this is just fun to quickly run through. So place our firefighter here. So basically I'm cutting off the fire at each step just in the nick of time. And notice that I didn't even use a single vertex from the importance separator. So that's sort of the contrast in terms of why using importance separators is not enough. However, we will see that importance separators can still be useful in certain special situations, but that's something we'll come back to in a moment. Let me just talk a little bit about tight sequences, because that's the notion that's going to eventually turn out to be useful. So again, we are looking at XY separators, but now I'm looking at a sequence of them in order. So the first one, if you want to be technical about it, would just be the set X, but maybe here's the first serious one. So the separator is actually the pink set, and the yellow set is the reachability set corresponding to the pink set. And here's a whole bunch of them. And such a sequence of separators is called a tight separator sequence if it looks like this, which is to say that the reachability sets are contained in one another like Russian dolls pretty much, and also each of these separators are minimal, and most crucially there is nothing in between that is a minimal separator. So if you look at this region here, which is loosely speaking the space between two consecutive separators, there isn't a minimal separator that's sitting entirely in this region. So that's why it's called a tight sequence, because somehow when you look at the sandwich between two consecutive separators, you're not going to find any other separators. Okay. Surprisingly for me at least, as someone who's seeing this for the first time, such sequences are actually easy to compute, and you can actually compute them by just computing a sequence of importance separators. So while finding all importance separators takes time, if you just wanted to find one, that's something that you can work out in polynomial time. So just finding one importance separator between x and y, and then recursing by saying I'm going to look for an importance separator between s and y, that's what gives you this sequence. So these sequences are not hard to construct, and they turn out to have several useful properties, and we will We will see in a moment why they're useful for our situation. So before trying to describe the algorithm in the general setting, which I will only sketch briefly, let me talk a little bit about trees, because that's where our initial intuition about importance separators actually turns out to be accurate. So if your graph is a tree, then let's just assume that, let's just root the tree at wherever the fire is starting, right? And so I haven't labeled it, so I'm sorry about that, but just imagine that the fire starts at the top. And suppose somebody comes along with a firefighting solution, which, well, if you looked at the vertices where the firefighters are, it's not an importance separator, which means that there is presumably another separator that covers the one that you started with. And it's not very hard to see that you can actually push the firefighters from the separator that you started with to the corresponding points on the importance separator. And the reason we need the graph to be a tree for this argument to work out is because you can make that association pretty cleanly when your graph is a tree. So there is essentially a unique path from where the fire is to the separator that you started with, which without loss of generality is a minimal separator. So there's just going to be one clean path from the source to every green vertex and one clean path from the source to every red vertex, which is the importance separator. And it's not very hard to sort of adjust your strategy so that it settles down on an importance separator. One slight issue with this would be that you are probably not optimizing the number of burned vertices. So by moving to an importance separator, you are letting more vertices burn, but it's just that it's faster to find a solution compared to the general algorithm that we have. If we just tried out all importance separators and tried all possible firefighting strategies on these importance separators, it's just a very simple algorithm. Let me just. Okay, so I wanted to speak a little bit about the issue of kernelization on trees. So for any problem that's fixed parameter tractable, the immediate next question that we usually ask ourselves is, does it have a kernel? In other words, can we, so the premise is still that we have a parameter which is smallish, and we want to know if we can transform the instance in polynomial time to a different one which is much smaller. So can we do this quickly to be left with a small instance and do it in a manner that doesn't disturb the instance? So which is to say, we want a polynomial time algorithm which transforms our input instance of size n to something that is a pure function of k, something whose size is a pure function of k, and we want these two instances to be equivalent. So this is a really nice formalism for capturing pre-processing, which is something that people in the real world do all the time. We were talking about why SAT is considered completely solved in the real world earlier today. So this is one of those situations where we're trying to come up with an adequate formalism for capturing why certain things work so well. So the idea is that before solving the instance, can you crunch it up a little bit efficiently? And notice that the presence of a parameter really helps you build this formalism, because if you didn't have k, just insisting that the size of the instance strictly reduces doesn't leave you with a useful definition, because no NP-hard problem would have an algorithm, a compression algorithm like that. So the news is, so this is the size of the kernel is just the size of the instance that you're able to bring it down to. And as is typical, the holy grail in kernelization is to come up with kernels that are polynomial in size. So the question is, does the firefighting problem have a polynomial kernel, at least when restricted to trees, which seems like a nice simple case to handle, and unfortunately the answer here is in the negative. I was going to say a little bit about how we are able to show something like this. What is the framework for showing negative results for the existence of polynomial kernels? But I think in the interest of time, maybe let me see if I want to come back to this. at the end. So I'll just say a little bit about the algorithm on general instances. So recall that we were talking about these tight separator sequences a while ago. So just to bring this to the scenario that we are interested in, let's just reset X to S. So S is the source of the fire and Y is C, that's the set of critical nodes that we are trying to fight off. So first observation is that if the length of this tight separator sequence is more than K, where I'm using K to denote my firefighting budget, I'm allowed to place K firefighters, that's my parameter. So if the sequence has length more than K, then I'm in fact done, because that gives me enough time to just place firefighters on the last separator. Because remember that the fire is starting from here. So forgive the copy paste error, this should have still been S and C, but anyway, the fire is starting from here, and notice that because this is a sequence of separators, the fire must actually jump through each one of these hoops to reach the critical set. This is like an obstacle course that we have just built and that we are able to see, because if there was a way of burning a vertex here starting from here, bypassing one of these guys, that would not qualify as a XY separator, because that would just mean that you have a burning path that just is not touched by this guy, which is a contradiction to the definition. So that's the situation. Any burning path that's trying to get here must jump through each one of these hoops, which means that if we have sufficiently many of these hoops, then we buy ourselves enough time to come up with a peaceful solution. Again, this is not particularly optimizing for minimizing the overall damage in the graph. So by just placing firefighters at the very end, I'm really being very partial to these critical nodes, and I'm letting the rest of the world burn. Okay, so that's a little unfortunate, but it works for the sort of the formal setting we are in. I'm not sure if I would recommend implementing this as is, but anyway, that's an easy situation. Now, if also the size of the smallest separator between X and Y is less than K, then we can reject this instance, because as we said before, the set of vertices that have firefighters on them are legit XY separators, where X is the source of the fire and Y is the set of critical nodes. Therefore, if the smallest separator is beyond my budget, there's really no hope for doing anything, which means that the total size of these pink boxes is now bounded, because each one of them has size at most K, plus the number of them is also at most K. So what I'm looking at here is sort of something that's bounded, and bounded as a function of K, and therefore manageable. And now what I'm going to do is what we folks usually do, which is a pretty brutal brute force approach. So you're just going to like guess like there is no tomorrow. So we're just going to guess what's going on these pink boxes. We're going to guess exactly what timestamps do firefighters come on these pink nodes. So remember that the pink set is bounded. So if my budget is K firefighters, that means the total number of rounds is really 2K. I get to place a firefighter at every odd time step. So the total number of time steps is 2K, and for each one of those time steps, I'm going to guess in which box does this time step go? Where am I going to place the firefighter? So this is an arbitrary sort of, a sample guess that I've made here. So the first firefighter goes into this box, the second one goes there, and so on. Notice that when I declare a time step as belonging to a gray box, I can't pin it because the gray regions are unbounded. So I can't really pin down where exactly the firefighter is going to be, but I do know that the chap's hanging around somewhere here. Okay, so that turns out to be enough, because now what I can do is also guess the shape of the rest of the vertices which are not going to be protected. So I'm not going to be placing firefighters on them, but the pink The pink regions are small anyway, so I'm going to guess away even more. So I'm going to say these are the vertices that ended up as burnt at the end of the game. These are the vertices that ended up being saved at the end of the game. The protected ones, we have anyway made a very fine-grained guess. We've not only declared that they're protected, we know exactly when they got protected as well. So that's the shape of a guess, and now we're just going to recurse. So we're going to break this down into smaller instances. So basically, if this was a sequence of Q, this was a sequence of Q separators, then I'm actually going to chop this up into Q instances. And this is where there's a bunch of details that I'm pushing under the carpet. The point is that I need to carry over the semantics of my guess into the recursive subinstances. I also need to make sure that there is some concept of a measure that's dropping when I recurse. Otherwise, this is not easy to bound the overall length of the process. But it turns out that the notion of a tight separator sequence helps us with the measure. The fact that there is no separator that sits entirely inside the gray box. So remember we said that these adjacent separators are tight, so there is no separator that's sitting completely inside. That is something that's useful for showing that your measure actually drops, that when you go inside, you have a strictly smaller budget to work with. And then you have to do a little bit of gadgeting to encode the semantics of these labels to make sure that your solution here actually respects the global semantics. So you have to kind of throw in a few pretend vertices which force these guys to take on these roles, and then you recurse further. So it turns out that everything works out. But I'm not going to bore you with more details. I think I have just about enough time to make a few more remarks. One is that we also consider the spreading model, which apparently is useful in some situations, where at every step, not only the fire, but also the protection spreads BFS style. Okay? So maybe in some situations that model the spread of disease and vaccination, this is something that's useful, that the firefighters not only protect the vertex that they're literally standing on, but also in some sense the effect of their protection also spreads at every step. So now you really have two competing forces, but it turns out that this model is a little more expressive and can capture problems like dominating set, which are again intractable in the parameterized world. So at least as far as saving critical sets are concerned, this question, which seems very closely related, turns out to have a slightly different complexity. One thing to account for is also this notion of thresholds. So maybe a vertex doesn't get burnt when the fire hits it once, but only gets burnt when the fire hits it multiple times from multiple sources. I'll say a little more about this on the next slide, so I'll come back to that. As I've been saying throughout, I'm a little depressed about how many vertices we are burning just to save the critical guys. So accounting for multiple optimization objectives simultaneously would be so much nicer. We mentioned a few at the beginning. There are others as well that people like to consider. So I mean, there aren't all that many algorithms that account for them simultaneously. So this would be nice to think about, I think. When we think about optimizing the number of firefighters per round, so what is the smallest number of firefighters that you need to unleash to achieve, let's say, simply the objective of protecting the critical set? It turns out that that's a completely different problem. So somehow whatever we said about the separators in the tight sequence being bounded, all of that, at least thinking about it naively, all of that goes out of the window. So maybe this requires a fundamentally different approach. So that's again one of our open problems from this work. There was a nice paper called Making Lives Easier for Firefighters, where the authors discussed a whole bunch of graph classes on which this problem is tractable. Yes, this is the last slide, practically. So it would be nice to know if there are, so there is something called the parameter ecology program, where we want to know is the problem also tractable for graphs that are close to being tractable, in the sense of typically if you're k vertices away from being a split graph, then can I do something that's FPT and k? What if you flip the goal and you wanted to actually burn as much as possible? This is the situation where the process is modeling something like spread of information in a network. So if you're a businessman and you want to advertise on Facebook, you want to start the fire with a few key influencers so that the message reaches out to as many people as possible. And this is where thresholds make a lot of sense. So maybe I'm not convinced to buy something if one of my friends recommends it, but maybe if 5 of them do, then that flips a switch. So there's been a lot of study on influence maximization, but not necessarily of the flavor that we have seen here. So that's also something that's I think fun to think about and discuss. I'm sorry if I stepped over time, but I'm really done now. So thank you.